11. T-tests for two related samples. We can also refer to this as within studies design. So in this lecture, we're going to talk about what research studies would really be appropriate for repeated measures t-test hypothesis testing. Also, what this test really means is we're going to focus on the mean difference between two treatment conditions using repeated measures, t statistics. Of course, if you do reject your null hypothesis, determining effect size, and then re-explaining some of the pros and cons of repeated measures, and also with independent measures and a peek into matched samples. Okay. Please keep in mind with all t-testing, right? So we had two previous lectures with intra-t or like single sample t or independent t, right? The whole idea of estimated standard error. Of course, degrees of freedom, the t distribution, so that you should have access to like a t table. What does that four-step process look like when you do with, or when you deal with hypothesis testing? Quick insight there, it's the same as like z-scores and ANOVA and everything else, right? It's always that same the four-step process. And then assumptions, right? So obviously keep it independent. Homogeneity of variance, Fmax. If you're going to run that test, I like to use Hartley's and the Fmax table. Okay. So with repeated measures designs, always keep in mind that you are dealing with right, the repeating part of it, right? So focus on that word. Yes, you can say like, oh, is it within subject design? Yes, and that would be a great precursor to things like ANOVA or analysis of variance. So what you're doing is you're looking at two separate scores obtained from usually each individual. Okay, so yes, so you're looking at like you're grabbing a group, right? You're grabbing a sample, but you're using the same participants in both treatment conditions. So think like pre-test, post-test, before, after. So you really don't have a risk of right, that like the differences between these two participants because, well, they're the same people, right? So think of it like, okay, you're gonna have a group of 12th graders and you're gonna say, okay, I'm worried about, I don't know, stress that puts on for homecoming and right, and then I don't know, you have the holiday season coming up, and then you have your prom, and then you have, I don't know, you have, you know, your SATs and all these things that, you know, these crazy things that happened this last year in American high school, and you want to see like, okay, I have a new treatment that I want to see if this reduces stress for people. And so what you do is you grab a small group of 30 or 40 12th graders in this high school, and so you do the treatment on them, and then like you test them. You test just a small group, and so you take them aside and say August, and you test them and you write down their scores, and then you test them again in, I don't know, April or May, right? And you write down their scores again. And then you say, okay, I am concerned about their scores. Really what I'm looking for is that difference. So while in like the previous lecture, right, with other types of T-scores, you might have an N equaling 60, right? Because you grabbed 30 from this group and 30 from this group, and you're going to compare these between these two groups, and so you have 30 and 30 equals 60. So with this type of t-testing, right, you have this repeated measures design. You still have N equaling 60, but you only have 30 people. Because each of those people, each of those participants are giving you two sets of scores, right? So it's nice. It's a way of getting a lot of data, but not having to have a lot of participants. Okay. So structurally very similar to other t-statistics, right? So it's essentially the same as a single sample t. The main difference is you're really looking at that difference score, right? So again, you're not looking at like a raw score with an X or with a Z-score, right? And you're not really looking for like comparing this group to this group. You're looking at comparing that one person between like the after effect and before the effect to see if that treatment that you invented or you're testing out had an effect. Right? So you're looking at not necessarily a raw score, one raw score, you're looking at one score, the score now being the difference or that mean difference, because again, you're not dealing with one score, Z, you're dealing with that group, right, that you pull, that mean difference. Okay, so top left-hand corner there, you have your T statistic, right? So yes, and on the next slide, I'm going to break down like what it actually means. And yes, I know you're accessing this on the interwebs, right? So you don't have to memorize it. I don't know, maybe you do for some class somewhere. But what I want you to really look at is what are we doing with this equation, right? What we're doing here is we're looking at how far away is that mean difference scores that we pulled, right, from the sample. How far away is that mean difference group of scores from the sample from the population, right? Divided by the estimated standard mean difference. But what we're looking for is that variability, how far all over the place are the scores, right? And in effect, like how far away from that are those groups of scores from the population. Okay, so let's break it down. So the numerator, the top part, right? The numerator of that T statistic is measuring, what it's trying to measure is the actual difference from or between the mean data from like the sample mean data and the hypothesis mu data. Okay, the denominator, that bottom score there, is trying to measure the standard difference that is expected if that null hypothesis is true. And this is important, right? So really tune into this, right? Because if that null hypothesis is true, well, then your treatment really wasn't that effective, right? Because the whole goal of experiments, the whole goal of running a study is to see if you can reject that null hypothesis, right? You gotta kick it to the curb a little bit, because what you're doing then is you're saying that's natural, that's nature. I want to alter that a little bit, right? It's natural to be sick, it's natural to be stressed, it's natural to be sad, whatever it is, right? I want to see if my treatment can alter that, can have an effect, can bounce that off of natural, right? The null hypothesis is none, zero, no difference, right? The denominator is measuring that standard difference to be expected if that null hypothesis is true. We're going to follow that same four-step process that we always do with all hypotheses, right? So number one, state the hypothesis pair. So you're always going to have a null and alternative hypothesis. And I don't know, quick like little piece of good news preview. They're really short for this one, right? And then alpha level, right? With social behavioral sciences, alpha level is usually 0.05, usually a two-tailed test. Yes, I have a slide coming up that says yes, you can use a one-tailed test, make it ethical, and state the reason why. Okay, knowing that gives you a pretty good clue on what your critical region is going to be, right? So normal distribution, two-tailed test, you're going to have two critical regions. If it's 0.05, you split the tail. So 0.025 on this side, 0.025 on this side, right? Get out your t-table, right? You can find your critical region, also called like t-crit, right? And that's your bullseye area, right? So again, what we're trying to do is say, okay, this is the areas in that normal distribution. Once we do step 3, we calculate and determine our t obtained, or a t statistic, right? Or a test statistic. Does our t obtain fall within one of those critical regions? Because it's a two-tailed test, so we have two critical regions. If it does, yay, right? We can reject that null hypothesis. Because what we're saying is, sure, it could be random chance that my little sample group that I pulled and I did a treatment on, that they're just wildly different. They're statistically significantly this far off to this far left, right, from the mean or from the population mu. But sure, they could be that just randomly. But look how far off from the population average they are. They're really far off, right? So I'm going to make the decision. I'm going to reject that null hypothesis. I think it was, I'm pretty sure it was my treatment that had the effect. And then if I have that confidence, I can then usually run a Cohen's d. Okay, so like I said, the hypothesis statement, the pairs are pretty small for this one, are very short, very concise. The null hypothesis is the mu difference is 0, right? Again, what's the whole focus? What's the main point of repeated measures design in a t-test, right? Is there a difference? So the null hypothesis is there is no difference, or difference is 0. So mu d, right, is 0. The alternative then would be it does not equal 0. Okay. Yes, you can run a one-tailed test. So sometimes you have specific reasons why, usually ethical. You don't never want to increase someone's depression rates. You want to run a one-tailed test. Okay. So it would sound, depending on which way you want the tail to fall, right? So null hypothesis is mu difference is less than or equal to 0. Alternative hypothesis is mu difference is greater than 0, right? Please note that if you do choose to run a one-tailed test, you need to have that all the critical region in that one side or the other side. Also note, because you're doing that, your critical region is going to balloon up, right? Because with a two-tailed test, you take that 0.05 and you cut it in half. So now you have 0.025 here, 0.025 over here. If you only have a one-tailed test, you now have all 5% on one side. So you have a much greater chance of rejecting the null. You also have a much greater chance of blowing a type 1 error, saying that you found the cure. You really didn't, right? So just note that. Okay. This is just a very general situation of running like a repeated measures t-test. Okay. So say you select a sample of 4 people from the population. You measure each individual twice, once in treatment 1 and once in treatment 2. Yes, you care about their scores, but what you really care about is their difference. Okay, so take a look over here, far left-hand side. So you label your subjects A, B, C, and D. Okay, so first time you measure them, subject A scores a 10. Great, notate that. Second time, you give them the test or evaluation or assessment, whatever you want to call it. Subject A scores a 14. They have a difference of 4. So you definitely write that down. So that's when you write down everything. But you really focus on the 4. Okay, subject B. First time they score 15. Okay, write that down. And then the second time go around, they score 13. And it's okay, they have scored -2. And again, we don't care if it's positive or negative because what we're focusing on is how far away from the mu difference they are. What's the mu difference? The mu difference is 0. Because what's the null hypothesis? The null hypothesis is 0, right? Because if their treatment had no effect, what would the difference be? If my stress level was at a 10 in August, you gave me a treatment and it had no effect, what should my stress level be later? Should be 10. No difference. If my stress level was 15, you gave me treatment and had no effect, where should my stress level be afterwards? 15. No difference. But you see here how there is a difference. Sometimes they go up, sometimes they go down. Okay. So you keep going. Subject C. First time you gave them the test, 12. Second time you gave them the test, 15. Up by 3. And you keep going. Subject D, 11 and 12. And you just, okay, so you see how we don't care about their pre-test, post-test. What we really care about is their D. We really care about their difference. Okay, so what we're doing is we're computing the different scores, D, for each individual in our group, in our sample pool. So the sample of different scores is intended to represent the population because you did your due diligence and you actually did like a good sample poll, right? You didn't just cherry pick your participants. You I had an accurate sample that I pulled from, okay? Please note that you're using the sample of the different scores to represent the population of different scores. You're not just doing one raw score. You're doing like a distribution of sample means, right? You're doing the groups of people. Okay. The observations from within each sample must be independent, and the population, the distribution of sample scores must be normal, or at least approximate normal. And again, when in doubt, just pump up your sample size. I know, easier said than done. Get it close to 30, and they're usually pretty good. Okay. if you're like, woohoo, I rejected my null hypothesis, my treatment effect works, you need to take the next step. Find your effect size. Most commonly used ones to measure repeated measures t, and all t's really, estimated Cohen's d, and percentage of variance accounted for. Okay, with estimated Cohen's d, you're really saying like small, medium, large, right? So when you write it, so you're going to calculate it, it's going to give you, right, 0.3, 0.4, 0.5, whatever. So when you report it, you need to report the number. So Cohen's d equals 0.7. Then you also need to say, like, linguistically what that means, large effect size. Percentage of variance accounted for tells you how much you can accurately attribute your treatment back to, or how effective your treatment was to moving the needle, if you will, right? So if you were to say, well, my treatment, if I ran this number and my percentage of variance accounted for came back at 60%, so 0.6, and I converted it to 60%, I could say, well, my treatment was in fact effective in lowering their stress. This graduating class had a lower stress than previous graduating classes. And I can say that their stress, the percentage of variance that I can account for their lower stress was about 60%. That's strong. That's strong evidence. And, of course, confidence intervals. Okay. When you're writing it, when you're reporting it, right, you want to include a lot of things. Obviously, mean, standard deviations for your both statements, like your written ones, and also any kind of tables that you ran. Also report your degrees of freedom, any significant levels, and effect size. And at the very, very bottom there, I have like an example in current APA formatting. Okay. I know you're getting sick and tired of me saying this, but sample variance. Okay. When in doubt, pump up your sample size. I know, easier said than done, but the size of the sample really does matter. It covers up a lot of issues that might be messing with your study. Things like standard error and wonky variance. Okay, so the size of the sample, mean difference. So if you have a large mean difference, right, what that's usually indicating is that you have a larger numerator, so it definitely makes that t obtained increase or get larger, right? Also with sample sizes, the larger the sample size, the smaller the standard error. It's denominator, the bottom side, right? So it's going to make that t obtained larger. And obviously with the sample size, it also has an effect on variance. It has an effect on power and type 1 errors and a lot of things. Okay, I want to talk a bit about variability. Okay, so say you reject the null hypothesis and you're happy and you're like, I'm going to publish, this is great. But then you look at variance and it's really, really hard. And you're like, well, I wonder if that has an effect on my study. And it absolutely does. Okay. When variability is small, that's great, because what you're saying is, yes, my treatment has an effect, and there's very small variability of scores. What you're saying is there could be a little bit of issue of how this person reacts to this treatment, how this person reacts to the treatment, but it's very small. The difference of the scores are clustered very, very closely together. Okay. So what that allows you to do is it says, yes, my variability is small, and so therefore my treatment effect is very significant. And the opposite's also true, right? When the treatment or when the variability is large, it makes your treatment less consistent because the difference is all over the place, right? The score's all over the place. It's very hard to replicate what you did. It's very hard to discuss what you did. It's very hard to, frankly, take what you did seriously, right? So I would say go back and look at the conditions that your participants were in and see if you can mitigate some of the outlying conditions and see if you can focus and try to determine if you can make it so what you're really doing is just isolating that independent variable and see if that creates a smaller variability difference, because that'll help with your consistency and will help with the significance of your study. Okay, let's talk about some advantages and a little bit of the disadvantages of repeated and independent measures designs. Okay, so some of the advantages of repeated measures design include that absolutely fewer subjects, half, because you're just using the same people, right, versus having to like use two different groups. Okay, also the ability to study changes over time. Your participants are going to age, right? They're going to, you're going to see growth, you're going to see progression. It also eliminates problems caused by individual differences. So barring traumatic life events or something really out of the ordinary happening, people are going to stay the same, right? So Julie or Jeremy or whoever, you're, Sarah or Jessica, they're going to be the same people now when you test them again. Yes, sometimes look over the disadvantages. Sometimes, no, they do change. Sometimes traumatic events do happen. Sometimes factors other than the treatment absolutely change participant scores. Right? Sometimes wild things happen. You just got to start again. Okay. And then obviously you have substantially less variability in scores because you're dealing with the same people. And this tends to have more power. Again, power is that likelihood of detecting real treatment effects, right? Lowering that chance of, having a type 2 error. Okay. Another thing that you kind of need to be worried about is this whole idea of order effects, right? So with repeated measures design is they've seen the pretest, right? So does that affect their score on the post-test, right? Think like the first time you watch a movie, you catch, 70% of the jokes, 70% of the the lines. Then the second time you catch more because you've seen it, right? So absolutely take that in consideration. Okay, match study designs. This is like the gold standard with repeated measures, because it takes everything that's great about repeated measures and it uses this different people, right? So it gets rid of order effects. It gets rid of them seeing it beforehand. Okay, so I'm going to use the example of twins, right? So it combines the advantage of independent measures and repeated measures. So it uses two separate samples. So think previous lecture, right? And think this lecture, right? So what you're going to do is you're going to each individual in a sample is matched one-on-one with an individual in another sample. Okay, so again, think twins. Participants are not identical unless they're twins to their match. I know twins aren't identical unless genetically they are. Okay. And what you're trying to do is you're trying to get them matchy-matchy as much as possible. Okay. And then what you're going to do is you're going to test them at the same time. So really what it does is it blends last lecture and this lecture together. Now, very hard to do, but worth it.